Here's another problem that pops up from time to time. It's very similar to another video we had. It's a hanging block M1 and a block sitting on a table, but the difference between a block sitting on the table is there's friction now. So I've drawn the surface purposefully rough in there, and my implication of this here is that there's going to be a mu now that sort of exists between M2, the block, and the table right there. Okay, so the answer is the same. The answers we're going for are the same. What are the accelerations and what are the tensions? So same type of answer desired. The problem might want other things, but usually they stem from knowing the acceleration and or the tension in the problem. So once again, I've got two forms of Newton's laws. I'm going to identify forces. I'm going to set up a sign convention. Then I'm going to fill in equations 1 and 2, and now it will pop my answers. So off we go then. Let's identify the forces. So if I look at M2 here, there's definitely weight in M1. There's definitely a weight down M1G. And there's going to be an upwards tension pulling up on that one. Over here, rope always pulls away from its point. Tension always pulls away from its point of contact in a rope, so there'll be a T over that way like that. Now there has to be, since there's friction in the problem, there has to be some indication of which direction the object's moving in. Let's just say that in this particular problem, we don't know this. You'll have to figure that out for yourself based on the actual problem you're working on. Let's say this double arrow indicates that someone somehow told you that M2 is moving towards the right. That means M1 is moving down, but you need to know that information because if M2 is moving to the right, that means the frictional force must be back this way because friction always opposes any motion like that. So there'll be your frictional force back like that. So there's one of the core differences between this problem and one that appears in earlier videos. You have that frictional force and you need a little knowledge about the direction it's moving in there. So there you go. Next thing I do, I've identified the forces. Actually, there's just two more because if you want here, you can write that M2G has its weight on it right there. And because it's sitting on a surface, the molecules on the surface are flexing. So there'll be a normal force up on that one as well. So there you go. So what I've done now is I've identified all the forces on all the blocks. I've completed step 3 here. And now I'm ready to go on to step 4, which is find the signs, right? The sign convention in there. Okay? So M1G, we like to call that negative, but I'll just sort of randomize the problem. But I'll just call it positive this time. Even though down is usually negative, it doesn't have to be. I'll call it positive. If down is positive, up is going to be negative. So this T up here is going to be negative. And we know that tensions on opposite sides of the rope have opposite signs. So if that's negative, that's going to be positive. Now I'm looking at M2 going, looks like right is positive, so left better be negative. So there's a sign convention. I got the sign convention locked in throughout the entire problem now. And if you want, the vertical force on M2 here, you can call down negative, like that. Looks like my pen's dying. We can call down negative, and we'll call up positive. So this will be a minus sign right here. That'll be a plus sign right there. So now I've completed step 4. I have all the signs on the problems. So what we'll do now is now that we're finished steps 1 and 2, recognizing Newton's laws are available for us, we've identified the forces and the signs, go to step 5, which is fill in equations 1 and 2. Let's see what we get. Do it mass at a time. Let's start with M2. Okay, so the x acceleration is the sum of the x forces divided by m, just a straight application of equation 1 right there. If I look at the forces in the x direction, I see a minus f and a t. So I can put in a minus f plus t divided by m2, and I am done. This is the x acceleration on mass m2. Equation has been formed. Newton's law has spit out an equation for us. I can also fill in the one for the y. And for this one here, if I look at the block, I have a normal force up and a weight down. So I have a plus n minus m2g over m2, and I am done with that. There's my y acceleration. So Newton's law, double application in the x and y direction for m2. I've sort of formed everything I could possibly know about it, the x and y acceleration now for that mass. Not quite complete because I don't know what friction or tension is, but we'll get there. Well, maybe we'll just do a little bit more work on M2 right now. One thing you include from M2 when you read the problem is the problem never said anything about this mass here rising up off the surface or digging down into it at all. And so if the problem initially starts with 0 y velocity here, and the acceleration in the y direction is also 0, that will guarantee the object will never lift off or dig into the surface. Vy is 0 and ay is equal to 0. So what we conclude then down here, if ay is equal to 0, that basically tells us from this equation right here that n must be equal to m2 times g. It reveals the strength of the normal force of that block sitting on the table. Maybe that's obvious and maybe it isn't. But what I can do with it now is because in this equation right here I have an expression for F. I need to know something about friction, and I know that friction is always equal to mu times the normal force. So the frictional force then will be mu m2 times g. So I get the frictional force, and now what I can do is I can just drop down this equation here and fill in a very complete and useful form of it without really any more ambiguity. Friction is minus mu m2g plus the tension all that divided by m2. If I put a big box around this, and basically what I have then is I have a nice equation for a sub x. I have an equation which describes the acceleration of this block left and right along the surface, including the friction in there. And if you compare this with the other problem in the other video that doesn't have any friction, you'll just notice that this term here has been added, and that's really the only difference in there. And our sign convention is different. So anyway, there you go. I've completely analyzed M2. Let's look at M1 now. So M1 is the hanging block. I could use equation 1 on this particular problem, but I don't see any x forces at all. I only see y forces. So I just can't use equation 1 even though it's correct and available. I'll drop down to equation 2, which allows me to find the y accelerations. So AY then is going to be the tension up plus m1g down. Again, I'm just adding those y forces. I see a minus t up and a plus m1g down according to our sign convention. And I'll have to divide that by m1. And I can put a box around that. I've just found the y acceleration for that hanging mass, m1. There it is right there. Tension up plus m1g down. There's a y acceleration. Now something that's not on the list but requires a little bit of common sense and some intuition on your part to continue on with the problem there. If I look at it, m1 and m2 are linked by a rope. If m1 accelerates downwards at say 1 meter per second squared, m2 must accelerate rightwards 1 meter per second. Alternatively, these two objects are connected by a rope. Their v and a must always be the same. So if I look at it, what does that do in the equations? Well, ay is the vertical acceleration of the hanging mass. There it is right there. And ax is the horizontal acceleration of the box on the table. But they are the same because those are the two accelerations that are linked by the rope. So both of these equations here are exactly the same. So you could say drop these symbols off and just say this one's equal to some acceleration and this one's equal to some acceleration. You could just do that. And if you did that, you get an acceleration term, or alternatively, you could just set the two equations equal to each other, which is what I'll do. So I'll say I'll get minus mu times m2g plus t over m2 equals to minus t plus m1g over m1. You put a huge box around that. I've just equated the two equations using an intuitive physics fact that two objects related by a rope must have the same acceleration. And so if I equate these two equations, I get a big equation there. And if you look at it very carefully, if you do some algebra, like in particular, multiply through by m2, then multiply through by m1, I believe you should just be able to solve that for the tension T. And there you go. You'll be able to get the tension in the rope. There's your first answer. And just like the other ones now, I think this happened in other videos, that if you have this tension T here, you have this variable, you see it sitting right there and right there as well. You can plug this T either into this equation or this equation, and since that involves A now, you do a little bit of algebra, and the acceleration of the system will pop out. You can get the acceleration to come out right off. Another way of sort of using the equations, if you didn't quite like that approach here, is when you recognize that AX and AY are the same, because these two objects are linked by a rope, you can sort of come over here and say, you can sort of rewrite the equations. You can say A is T minus M2 mu M2G over M2, and then the other A over there is equal to, say, M1G minus T over M1. These are what those two equations would become when you actually recognize the acceleration is the same. And if you look at it now, this is nothing different than what we just discussed, but you have two equations and two unknowns. You don't know T here or here, and you don't know A here or here, but you have two equations. So whatever procedure you're comfortable with, either substituting or figuring out some other way of doing it, just solve the two equations and two unknowns, and from this set of equations, you will also get A and you will also get T. And again, there's no difference in the ones you'd get over here, just this is a slightly different way of solving for the same thing. So there you go.